In the previous video, I mentioned that the Bronsted-Lowry theory has conjugate acid-base pairs. So let's define what a conjugate acid is. A conjugate acid is the substance that's formed once a base actually accepts a proton. Okay, so the conjugate acid is going to have one extra H plus than the original base did. And then the conjugate base is the substance formed when the H plus is donated. Okay, so an acid will donate an H plus. Once it's donated, that's what's left over is your conjugate base. So we have a first example here. So in this specific example, you're given both your reactants and both your products. So you're going to look at your OH minus. It should pair up with something on the product side that only differs from the OH minus by one H plus. Okay, so clearly it can't be the CN minus because that it does not even have an OH in it. So it has to be this H2O, right? If you add an H plus to OH minus, you're going to get HOH, or how we normally write it, H2O. So these two, the OH minus and the H2O, will be one conjugate acid base pair. So over here, the OH minus is a base, okay? And then once it turns into the H2O, it has gained or accepted an H plus. So this is going to be our conjugate acid. And we can just abbreviate conjugate because it's kind of a long word. That's our conjugate acid. Now, back to the reactant side, you can't have two bases, right? So one's going to be a base, the other's going to be an acid. So this has to be the acid. How else could you figure that out? Well, it starts with H, so that's usually a good indication. And then if you take a look at the other product, CN with a -1, that's just HCN. Once it's lost, it's H plus. Okay, so the CN -1 is your conjugate base. So two hints. Your base and your conjugate acid and your acid and your conjugate base, they can only ever differ. Those conjugate acid base pairs can only ever differ by one H plus. So if it's different than that, something's off. You don't have your conjugate acid base pairs locked down yet. And then the second thing is your overall charges. So here we have a -1, okay, and here we have a 0. So we have a -1 on this side. And then on our product side, we have a 0, and then we have a -1. Okay, for a total of -1. Your total charges have to add up to the same thing on both sides. Otherwise, you've made a mistake. So here's our second example. It says to predict the products and then label the conjugate acid base pair. So here we're not given both the reactants and the products, but we are told which of our reactants is the acid and which of our reactants is the base. Okay, so let's start here. Knowing that the NH4 plus is going to act as an acid, it means that it's going to be a proton donor. And I know that because that's the definition of an acid. So that means on the product side, we're still going to have an N, but instead of 4 H's, we're going to only have 3. And if we're losing an H plus, this means that this is just going to be a 0 charge, which we really don't have to show. And then we look at our base, and the H plus can't just disappear, so it gets transferred instead to our base, which is a proton acceptor. So it's not going to be H2, it's going to be H3O. And since an H plus was added, we have to give a plus sign there. By the way, these are all aqueous except for the water would be a pure liquid. So make sure it's balanced. It is. These are always going to be easily balanced because you're only transferring an H plus. And make sure the charges match on each side. They do. Okay. So your acid turned into the NH3. So we'll call that the conjugate base. So it's what's left after the H plus has been donated. And then your base turns into the conjugate acid, which is the hydronium ion. Remember that word, the H3O+. So now we'll do another example of this type. So we're going to predict our products. Again, we're told what is our acid. It's, in this case, the H2O. So that means it's going to be a proton donor. So if it donates a proton, we're going to be left with OH minus, or the hydroxide ion. And then that proton is going to go to our base, which is HPO4 2 minus. So we won't just have one H here, we'll have two. So H2PO4, and then you have to adjust the charge. So a -2 plus 1 from the H plus gives you just a -1. Okay, just do a quick double check. Over here we have a total charge of -2, and on the product side we have -1 and -1, which is -2. So that checks out. And then this base turned into the diphosphate ion. So the base is always paired up with the conjugate acid. Okay, so this is going to be our conjugate acid. And then our acid turned into the hydroxide ion. So that's going to be our conjugate base. Remember, these pairs that I'm doing, when I draw my little brackets at the bottom, they can only ever differ by one H+. And the last thing I want to talk about is this term amphoteric. If you noticed in the last example, water was a base, and in this example, water acted as an acid. And water is not the only substance that can act like this, but it's a pretty notable one. So if you think of like an amphibian can live both on water and or in water and on land. So ampho means kind of both. So amphoteric is a substance that can act as both an acid and a base. So you should know that as a vocabulary term.